Yeah, welcome back to Microeconomics YouTube channel. In our last class, we were able to cover descriptive statistics and unit truth test. Yeah, there was something I wanted to mention before the end of that class, which I couldn't mention for one reason or the other. And that is under your first difference in your unit truth test, in your first difference table, the one I kind of taught you how to sketch. Okay, the worst thing that must happen, or the worst thing that should happen for you to be able to use the ARDL is that under your first difference, everything here, the remark for all of your variables is significant. All of your variables is significant. S. That's the worst thing that should happen. If there is any of the variable where you have NS that is non-significant under first difference, that means you can no longer use ARDL for the estimation of this particular model. Okay, so just if you have a variable that is not significant, it is just better for you to find another proxy for that variable and use it. Sometimes research is about manipulation. It is what it is. Okay, so not just to give yourself too much problem, just look for another variable you understand and include it there. So from there we are moving on to bounds test. So bounds test is the test that make you to know if there is cointegration among your variables. So among your dependent variables, maybe variables, whatever. Okay, and your independent variables. So it makes you know if there's any long-run relationship between them. Okay, so when you say long-run relationship, it's the same thing as saying there's cointegration. So if you hear there is cointegration between these variables, so that means in the long run they are also related. Okay, so now there is a decision rule for bounds test, just as some other stuffs in your analysis. The decision rule here is that your F statistic, okay, must be greater than the critical value of your upper bound as 5%. Now the thing is, by the time you use if-use, or I can only speak of if-use, speak for if-use or of if-use, I don't know about others, the way they present theirs. By the time you use if-use to run your bound test, which is under your coefficient diagnostics, okay, test, by the time you do that, the way the results be displayed, you're gonna have the F stat right on top there. Okay, you can be 6.5 for whatever value it is, and you're going to have your critical values as 1%, 5%, and 10%. Then your critical values are going to be under I0. I0 is the lower bound, and you're going to have I1 upper bound. So you're going to be having like 2 critical values per each level of significance. So for 1%, for example, you have critical value for the lower bound I0, you're going to have another critical value for the upper bound I1. Okay, for 5% the same thing, for 10% the same thing. So you'll be having something like 6 critical values. Okay, so now what's the decision rule? The decision rule is that if your F stat, okay, your F statistic is greater than the critical value of your upper bound at 5% level of significance, so just go to your critical value under I1, check the value there, you can compare it with your F stat. So if your F stat value is greater than that value, definitely there is cointegration, which means that there is a long-run relationship among your variables in that particular model where there is cointegration. Okay, there is presence of cointegration in the model, something like that. Now, okay. Now the other thing is if your F stat is lower than the critical value of your lower bound, okay, or you're at your lower bound or whatever at I0. If your F stat is lower than it at 5%, because what we are using is 5% level of significance, then there is no cointegration. Okay. Now, if your I0, your critical value of at your under your I0, okay, or your lower bound critical value, if your lower bound critical value as 5% is lesser than the F stat, and the F stat is lesser than the critical value of the upper bound as 5%, that means you have an inconclusive result. So you can't tell if there is a long-run relationship among the variables or not. Okay, so that's not about that. So just understand this decision rule. So from there we move on to number 4. Okay, your ARDL model estimate. So if we've been able to ascertain that there is a long-run relationship, okay, by the time you're estimating your ARDL estimate, you'll be having short-run estimates and long-run estimates. Okay, I think ordinarily you should just have short-run estimates. So I don't even know if it's going to be called short-run estimates. Okay, you're just going to have an output displayed in front of you after you run your analysis. But if you've carried out your bounce test initially and then you've been able to realize that there is co-integration among your variables, okay, so what you have to do, okay, is for you to, I think it's still under coefficient diagnostics that you go to. Like I said, there has to be links, okay, video links, YouTube links that will be included in, the description of, this video or the videos under analysis, okay, so that will teach you how to check all of those things. Even if you can't do them, maybe you don't have the software or something like that, or you don't have a computer, at least that will teach you how these things are, okay, and how they apply to your particular project. So you go to, I think you go to your coefficient diagnostics and co-integration and long run stuff like that. So if you're using it, use 9, something like that. So under co-integration and long run, whatever, you click on that. So your results is going to display, and the first one is going to be your short run estimate, and under it are going to be having your long run estimate. Okay, so which means that you create a table just like the one that you did for unit root and descriptive statistics, and under a table you have your variables, okay, coefficients and the p-values. Okay, so for your variables, this is not the way they are going to display. Okay, not exactly like this. There are going to be other things: standard error, R squared, Dublin-Watson statistic, or whatever it is called, then whatever, a lot of things. Okay, so but what you really need from those things are unique coefficients of your independent variables. Okay, you need their p-values to tell if they are statistically significant or not. Okay, and you need standard error. So some people, standard error, so you put down in bracket underneath the coefficients. Okay, standard error and stuff like that. Okay, so for example here, I didn't run anything, I didn't do any analysis, okay, but I'm just using this to explain. For example, I have LI, which is lean innovation. All right, under lean, no, this should be lean inflation. This is lean inflation, and this is lean innovation. Now there are other things. All my variables are going to display. So inflation, innovation, all my independent variables. Inflation, innovation, human capital, government expenditure on health, and all of those independent variables that are going to show here. So I'll then pick them. So I'll pick, now the thing is, by the time your results are out on your screen, so sometimes you might see the lagged value of your dependent variable. For example, you have lean GDP, okay, so in some of the results you might see lean GDP into bracket -1, that is the lagged value, okay, the previous year value of lean GDP, which is telling you that lean GDP, the previous value of GDP, has impact on the current value of GDP. Okay, but because in your model, okay, that you've written out, okay, prior this period, in your model you don't have lagged value of the dependent variable, so you exclude it when you are drawing your table for your short run estimate. You don't include it. Okay, so as many you add lean GDP here plus alpha 1 plus alpha 2 lean GDP -1, that is when you can now use the lean GDP -1 value that you saw, okay, from the output of your results and stuff like that. But since it is not in your model, you exclude. So you might see stuff like that. You might even see lean GDP into bracket -2. Okay, so you might see lagged values, different lagged values like that in your output, but you just pick your own independent variables, the variables that are in your model specification, just pick them, create a new table. So one thing that I do when I'm doing analysis is that I try to have like 2 documents. So one will be for the proper analysis where I'm writing these things in a beautiful way, and then one will be for like a junk document, so something like a junk document. So for every output, or almost every output, or every important output that is generated from eViews in that raw form, so I just copy it and paste it there in case my supervisor wants to ask me, or maybe the supervisor of any of my clients that I'm working for wants to ask them that, okay, how did you get this? So you can just show them the document. Okay, these are the raw data that I got when I was estimating when I was conducting my analysis using eView. So I kind of keep them in a different document, understand, just in case. They've never asked, I don't think. I've not done so many analyses anyway, and they may never ask, and they may ask, you understand, but just do that. Your proper file, your proper analysis file will contain stuff like this in a neat way, while the junk file will contain all of those. That doesn't mean you don't arrange your junk file, but then it's going to look like junk too, because it will be a lot. Okay, to be a lot, and raw form of data, so it's not as if anyway. So that's that about that. Now in my okay, so I was trying to explain. So here now I can see that the coefficient of inflation is negative. All right, so inflation is negatively related to Nigeria's economic growth or Nigeria's GDP. So as since I'm using lean, okay, that I've logged all of this stuff, okay, so the interpretation is that in 1%, so I eventually wrote it down like the model specification. Then GDP is equal to the constant, which is this. Okay, whose interpretation is that if every other variable in the model were excluded, if they were zero, okay, then GDP is going to be positive, it's going to be equal to 100.29 whatever. So that means there's still going to be economic growth in the country if I should exclude all of the independent variables that are in this model. So there are still other factors outside the independent variables in this model that are responsible for a positive economic growth in Nigeria. This might be negative too. Okay. And it also represents the intercept of the regression line. Okay, so plus lane I, so lane innovation. Innovation is 1.2160, so 1.2160 lane innovation. Your own might write your results in 2 decimal places. Okay, it's fine. So lane this. So this is telling me that 1%, a percentage increase in innovation would increase GDP by 1.2, approximately 1.22%. Okay, a percentage increase in innovation would lead to an economic growth of 1.22% on average. Okay, because when we're talking about regression, we're talking about mean value, conditional mean value. You understand? Expected mean value. So on average, that's the way to interpret. On average, okay, on average, if innovation were to increase by 1%, there will be an approximate 1.22% economic growth in Nigeria, or increase in Nigeria's GDP. Okay, so inflation is negatively related to Nigeria's economic growth. On average, 1% increase in inflation, because it's minus, would reduce Nigeria's GDP by 0.01%. You understand? So that's not the end. You remember that there are other independent variables, so you add them. Okay, I guess I should just put them like that. So plus something, plus something, plus something. Okay, so that's all. So there's no need to add the error term in the final output representation. So that's about that. Now, after you're done with your ARDM model estimation, so if there was co-integration, so that means you do the other one that I told you about. So you have to go and find long run estimate. This is short run estimate. So you have another table for long run estimate. Okay, so your long run estimates, the variables you pick. So it's going to be something like this as well, but what you're going to have on top here is long run estimate. And under each of these tables, you have to write the source, author's computation using if-use. Author's computation using if-use. You might have another grammatical construct. It's okay. All right. So after that, we move into our diagnostics. Okay. So under diagnostics, I really want to talk about this. Under diagnostics, just talking about the assumptions of OLS. Okay. Now there's assumption of linearity. Your model has to be linear. Okay, for you to carry out regression. Then there must be your error term have to be almost stochastic. Okay. Then after that, you have your error terms also have, or your residuals, how to have a normal distribution. Then there must be no multicollinearity of your independent variables or of your regressors, and there must be no autocorrelation of your residuals or of your error term. Okay, now you would also have to carry out these diagnostics, okay, one by one. They are not so much, and they have their own respective decision rules. All right, let's take them one after the other. I hope we don't run out of time. So under diagnostics, so you could be asked to test for normality. So normality test, serial correlation test, homoscedasticity, heteroscedasticity tests. talking about equal or unequal variance. And you have linearity model specification tests. Okay, you might also be asked to look for your multicollinearity test. You understand? So I didn't include that. Of course, not everything can be in a particular video, but now let's go into the stuff. Now, under normality test, so normality is to help you know if your residuals, your error terms, if they follow normal distribution. Okay, so when we are saying normal distribution, we mean are they like this? Okay, where they have flat tails and flat tails to the right, flat tails to the left, but in the middle, the middle region happens to have most of the values. Okay, something like this. So hope they are not something like this. You understand? So how do you know if your residuals are following if they are normally distributed? Okay, so what you have to do is go to your residual diagnostics, because of course I'm talking about residuals now, and that is obviously after you've estimated your results. So after the first section that we just left, the short run and long run estimates. So after that, just from there you can move into your residual diagnostics, and you are going to see normality test. Okay, so click on it, then you're going to be having a histogram. Okay, and for the way to know if it has because you might not, looking at it, you might not be sure if the error terms are normally distributed or not. Just look at your Jacobera statistic, your JB statistic, Jacobera statistic, whatever value is there. Okay, is it greater than 5%? Its probability value, the probability value of your Jacobera statistic, is it greater than 5% or not? Okay, so if it is greater than 5%, that means it is not significant. Okay, it's just the same thing as what we've been doing. It is not significant, and as a result, okay, you are going to if it is not significant, okay, it simply means that you are going, okay, you will not reject the null hypothesis, okay, that says that your residuals are normally distributed, or that your residuals follow normal distribution. Okay, usually H naught will contain what you would like to see, something like that. I don't know if I'm saying what is making sense. So H naught is normal distribution. Alternative hypothesis is that no normal distribution. I'm not saying you're going to write it like this, I just want you to understand it. Okay, so H naught, you can say H naught, that's the null hypothesis, residuals are not normally distributed, or residuals are normally distributed, or residuals follow normal distribution. Okay, just that's the proper way to write it, but I'm just kind of summarizing stuff here. So that's why I just wrote normal distribution of what. Okay, so residuals are not normally distributed. That's the alternative hypothesis. So you look at a Jacobera statistic, then the p-value. If the p-value is greater than 5%, that means it is not statistically significant, and as a result, your residuals are normally, distributed. Okay, or they follow normal distribution, and we fail to reject the null hypothesis as a result. Okay, so you are done with that. So the implication of this is that if your residuals are not normally distributed, your estimates, the one that you got before we got to this point, your estimates are likely far away from the true estimate. What you are doing is regression. We don't really know the true estimate, but whatever estimate that is obtained through the regression analysis, if they follow the assumptions, okay, we expect that the expected value will be very close, like the estimates, okay, your b1 beta 2 beta 3, or your alpha 1 alpha 2 alpha 3, your alpha naught, whatever, so their values will be close, okay, to the real value. All right, but if your residuals are not normally distributed, that means those estimates will be far, okay, they may not be the true value, all right, or they may be very far from they can't be the true value, okay, or is I don't know how to put it, but they are incorrect. They can give you incorrect estimates. All right, so do I have an example of that? Do I have an example, or maybe when I move into auto correlation. Now B, that's not about that. Now B, for serial correlation, so use your LM test. Here use Jacobera LM test here. So it's still under residual diagnostics that you go to. So your null hypothesis is that there is no autocorrelation of residuals, or there is no serial correlation of residuals, or residuals are not autocorrelated, they are not, is it serially correlated? No, sorry. Okay, so after you conduct your LM test, you go to your what you are looking for is where your prob chi-square is. Okay, so the probability value in front of your prob chi-square. Alright, so if there's no prob chi-square, just choose the probability value. But usually I think under serial correlation you have like maybe different numbers or whatever, but just go to where your prob chi-square is, the p-value in front, that's the one you need. So under this, if your p-value is greater than 5%, so it simply means that there is no, your residuals are not autocorrelated. Okay, now what this means is that, now when you say autocorrelation, that means you have a residual or some of your residuals that can how do I explain now, that predict another residual. Now let's say after you've done your regression, along the line an error term E1, okay, happens to be equal to 0.5 E2. Okay, E1 happens to be 0. Normally when we're writing out the model, we write ET. Okay, now that ET can be a lot, so you have E1 being 0.5 of E2. So what it means is that you kind of have a part of E1 in E2 or a part of E2 in E1. You understand? So what that is going to lead to is an overestimation. Okay, your estimates are going to be more than what they usually are. Okay, and okay, you may not understand this. Now let me say you have sales and advertisement expenses. So you are doing a regression, a simple linear regression on sales and advertisement expense. So sales equals sales LT equals alpha naught plus alpha 1 advertisement expenses. Okay, and then you now discover that your results gave you something like sales equals 150, when your values are in millions now. 150 million plus 5 million advertisement expenses. Okay, something like, I've named it. So sales, okay, was 150 million. No, I think it's 150 million. Okay, no, I think where did I write it? So 0.165 million plus 5 million advertisement expenses. So this was your results. Alright, so now you know that you'll be needing this. It's a company, so you'll be needing something like this to like forecast what your sales is going to be if you increase the advertisement expenses by a particular amount. So if you were to, okay, this might just be 0 points where all values are in millions. So if you were to, according to this regression model, if you are to increase advertisement expenses by 1 million, okay, by 1 million, so 1 times 5, 1 million times 5 will give 5 million. That means your sales will go up by 5 million, and then the company decides to like design policies to ensure that okay, they are able to raise the advertisement expenses by 1 million to generate that expected level of sales. But in the true sense of it, okay, outside autocorrelation, okay, the real estimate might be something like ST being 0.127 plus 1.1 advertisement expenses. So which means that if advertisement expenses were to be increased by 1 million, sales would rise by 1.1 million. So you can see that there is a big difference between you expecting a sales of 5 million and you expecting a sales of 1.1 million. Okay, so here you would have been expecting that you get 5 times, okay, in revenue of whatever you spent on advertisement expenses, but in the real sense of it, you barely get the same thing. Okay, just a doubling of your advertisement expense. So you get to wonder what is going on and stuff like that. So if there is autocorrelation, you are likely to have, an overestimation of your parameters. They are going to be more than what they are supposed to be. Okay, so I think I've mentioned when there's autocorrelation or not. So when the p-value in front of your prob chi-square, from whatever, if I'm right, is greater than 5%, there is no autocorrelation and you fail to reject the null hypothesis. But if it's otherwise, there is autocorrelation and you Is it fail to reject? Yes, and you fail to reject the alternative hypothesis. Now that's that about that. Now for heteroscedasticity test, you want to test if your error terms are heteroscedastic, if they have equal variance or unequal variance. So how to do that is you can use your arc test. I think they are these are not the only test. Okay, and use your arc test. So the H naught, for by now you probably just know how the stuffs work. So H naught is homoscedastic, that is not heteroscedastic. Now H1 is heteroscedastic. So when your p-value is greater than 5%, that means your error terms have equal variance, that is they are homoscedastic. And when it is lesser, that is when it is significant, when your probability value is significant, then your error terms are heteroscedastic, that is they have unequal variance. So now when we are doing regression, you have something like this. So the regression line, you have scatter plots. So the regression is the expected mean value, represent the expected mean value, conditional mean value of the dependent variable. Let's say there's y here and there's x here. Okay, so if there is equal variance, if there is equal variance, we have something like this, and then a scatter plots, something like this. They are close. Okay, the distance between each point is kind of constant. Okay, this is equal variance. But if they do not have equal, if they are heteroscedastic, so you have, this is your regression line. Okay, you have some like this, but they tend to have some like this. So the distance, okay, of the different points in your scatter plots, they are far. Some are close to the regression line, some are far away from it. So when you have something like this is heteroscedastic, there's unequal variance. Okay, that is, I think there's a way. I wrote it somewhere. Dispersion. So when I'm talking about variance, talking about dispersion, how far away or how close are they from the regression line? So you can see here that they are kind of clustered. Okay, and the distance on average is kind of the same. Okay, so when you have something like this, what it does is that it helps the predictive power of your model. Okay, it ensures that you are likely right. Okay, because what you are looking at is on average. Okay, so when you are predicting on average here, if advertisement expenses were to rise by 1 million on average, okay, sales revenue would increase by 1.1 million. But when you have something like this is the expected mean value, and look at how far away some points are from the expected mean value. So how would you be able to say on average you are going to generate this when it is possible, all right, that some points are going to be very far away or are far away from the main point. So you want to say on average for things that are so far from the average. Okay, so it becomes difficult to predict. So that is why your estimates are also not going to be correct. So they are likely going to be far away from what is what is true. So the desired stuff here is that there is homoscedasticity, that is your dispersion of the different points in your scatter plots are close to the regression line. All right, so this is what is desirable, homoscedasticity. So you are expecting that your p-value is going to be greater than 5, that is you are going to be having p-value greater than 5%, which means that your statistic is what? Not significant, not statistically significant. So, and that already tells you that you have homoscedasticity and you fail to reject your null hypothesis. I'm already sounding tired. Alright, the last one is linearity. So another assumption of the OLS is that your model has to be linear in parameters. Okay, it has to be linear in parameters because you'll be having a straight line. So linearity in parameters means that you should be having a straight line. Your regression line is a straight line. Okay, so if the parameters are not linear, you might be having something like a quadratic graph, something like this, and this is no longer the kind of linear regression you are doing. This is what you are doing. Okay, not this. So when you start having squared, when you have a quadratic equation like ax squared plus bx plus c, this is the kind of curve that you are going to be having. So you expect that the parameters are going to be linear. The estimates, the alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 are going to be, linear, right? That is, their highest power is going to be 1. So beta 1 highest power is 1, beta 2 highest power is 1, or something like that. So how do you test that? You use your Ramsey reset test. Okay, so some might call it linearity test, some might call it model specification test. Okay, that is the model correctly specified? You want to check if your model is correctly specified or not. Okay, so using the Ramsey reset test, your null hypothesis is that there's linearity, that is, your model is linear. So you are like, the desirable stuff here is your null hypothesis. And maybe in another research you may choose to say that your null hypothesis is correct specification of the model, that is, the model is correctly specified. Alright, so somebody might say just use linear, the model is linear. Someone else might say the model is correctly specified, so it's no problem. Alright, so the alternative hypothesis is non-linearity in model. The model is non-linear, or the model is not correctly specified. So the same thing, you need insignificance, statistical insignificance, for you to be able to not reject the null hypothesis. So that's what you just have to know. Statistical insignificance, that is, your p-value has to be greater than 5%. Okay, then so let's say we conduct this test and then we look at the value in front of this. Okay, I think that should be the case. And if not, just check your p-value. If you don't have something like this, then your p-value will be 1. And if you have something like this, you are likely going to have like 3 different p-values. So the one in front of this guy, so that's what you go and look for. Okay, so if the p-value here happens to be like 0.1562, 0.1562, so 1562 is already greater than 0.5. 0.1562 is greater than 0.05, so which means insignificant. That is statistically what's insignificant, right? Or not statistically significant. So we fail to reject the null hypothesis that says that our model is correctly specified. That is, the model is correctly specified. Do you understand? Okay, and if after checking our p-value we found that it was 0.0000, that means it is statistically significant. So if it is statistically significant, that means we fail to reject the alternative hypothesis, and then the model is non-linear, or the model is misspecified. What you want is correct specification of the model. Okay, so that's that under diagnostics. The remaining stuff is Q-sum test and cumulative sum test, and Q-sum square test. That's cumulative sum square test. Now it's just to check if the model is stable. Okay, so for your Q-sum test, by the time you carry it out, I think it's still under, that's under stability diagnostics. Stability diagnostics, no longer residual. Stability diagnostics. You're going to be having 2 lines, 2 red lines. The red lines represents 5% level of significance. So you're going to be having, is it 2 red lines? Is it 2 red lines or 2 blue lines now? I think, okay, 2 red lines. I think so, 2 red lines. So you'll be having the one for your model is going to be a blue line. So it's going to be if it is in between, right? It's even like this. Yeah, it might be like this. If it is in between, that means your model is stable. All right, that is what you want. Okay, which is that's about your model is stable. But if the blue line, if I'm right, whatever color this line has is color that this line is also going to have. So I think it is red. So if your blue line happens to come out of this a little and then come inside this, because it has come out of the 5% level of significance line, your model is not stable. So what you want is for your model to be stable. So for a Q-sum test, you want the blue line to remain within the 2 red lines for your model to be stable. Now sometimes it may not be like this. So when you do your Q-sum square test, which means that you've logged your model, okay, so the line may now be inside of it, which means that your model is now stable after you've logged it. So what you really want is for your model to be stable. So if the lines are outside the 5%, so it might not just be here, so it might also be here. Okay, you might come in out here, entering or not even entering again, whatever it is. Okay, so if you have anything that is outside of those parallel lines, okay, the parallel, I think that's better, but I don't even know what color the lines are going to be in whatever package you are using. So if the lines are outside the parallel lines, so that means your model is not stable. What you want is for your model to be stable. I'm not sure now that I'm recording this video, but I am thinking, even if your Q-sum graph shows that your model is not stable, your Q-sum square graph should show that your model is now stable. Okay, I think, but normally I think Q-sum graph should show that your model is stable, and Q-sum square graph should show that your model is stable. But if the Q-sum graph which comes before Q-sum squared is not stable, I think now that the Q-sum square graph should be stable. Alright, I am already very, very tired. So with all of this that we've done today, I hope that you'll be able to carry out your data analysis section by yourself, or at least be able to interpret your data analysis. You could give it out, you could outsource it to people like me. I've told you I'll do it for you, and I'm going to charge you. Okay, not so much though, just the required fee. You understand? But when the results are out, I hope this class will make you understand all of your results, that by the time you're doing your project defense, it's gonna be sweet. See you in the next class. Thank you very much.